Hello guys, and welcome back to my YouTube channel, Odavig Structural Hub. This is the #1 channel for structural insight and a place where you learn, build, and innovate. So if you have not subscribed to this channel, please subscribe and hit that notification bell so that you may be the first person to be notified when I upload a video. So without wasting any time, today I want to talk about the flanged beam, and this is the design of reinforced concrete to Eurocode 2. Remember what we did in the other session? We only tackled a simply supported beam that was rectangular beams. So today I want to tackle the flanged beam, and more so I will solve a simply supported T-beam design. So I want to emphasize on something, and this is regarding on the question that my subscriber asked me in a comment section. So I was asked to tackle examples regarding continuous beams, and I want to assure you that after we have done with this flanged beam, remember this is a simply supported beam, we will start what we call continuous beam. And continuous beam is a beam which is resting on more than two supports, and it has two spans and above. And we will do that as you requested in the comment section. So we will use the methods that you mentioned to analyze the continuous beam, and henceforth we will design such a beam. So some of the methods that you mentioned in the comment are: number one, we have the three-moment theorem. Number two, we have the slope deflection method, and number three, moment distribution method. So let's now go back to what we have for today. Today I want to talk about a flanged beam, and this is the design of reinforced concrete to Eurocode 2. So what is a flanged beam? This is a T-beam and or inverted L beams which are casted monolithically with the slab. Monolithically, it means it's a beam which is casted with slab continuously without any joint. We have diagram here which explain further what a flanged beam, that is for T and inverted L. So here is a T-beam. So as you can see, a T-beam, it is supporting slab on both sides, this side and this side. So, and it has a flange which is B, and then this is the thickness of the slab which is HF, and this one is the web. So this is the breadth of the web, or the breadth of the beam or the rib, and this one is the overall H. The same apply to this one. This one is the overall H, the breadth of the beam or the flange or the web, and this one is the thickness of the slab. So those are the two different types of flanged beam. And then you should know when are you supposed to design a rectangular beam and when are you supposed to design a flanged beam, which is a T or inverted L beam. So for example, for rectangular beam, you only design for rectangular beam if that beam is a secondary beam and it is supporting only the beam itself or the self weight of the beam and the loading on that beam. The loading can be the load from the walls or the partitioning walls. Also, you can design a rectangular beam as a precast beam. A precast beam is a beam which has been made in a factory and then transported to site for installation. And then this T and L beam, for example, a T beam is a center beam, and this beam is supporting both sides of the slab, on the left side and on the right side. So this is what we call T beam. And then the L beam, or inverted L beam, is a beam which is found on the edge of a building. On the edge of a building, it means it is supporting only one side of the slab. So you design such a beam as inverted L beams. So today I want to solve one problem, and this problem is a simply supported T beam design. We want now to see how we can come up with a design of a T beam for a simply supported beam. So I have the question here on the board, and the question reads: design and detail the section of a reinforced concrete T-beam given the following information. Number one, we have effective span is equal to 6 meters, and then spacing of T-beams is equal to 3 meters center to center. Number four, we have breadth of rib is equal to 250 millimeter. Number four, we have the thickness of lower slab is equal to 150 millimeter. Then the overall depth of beam is equal to 600 millimeter. Variable action is equal to 2.5 kilonewton per meter square. We have finishes 1.0 kilonewton per meter square. Unit weight of concrete is equal to 24 kilonewton per meter cubic. Concrete strength C2530. Then you have the cover is equal to 25 millimeter. And then assume any other relevant information. So let's see how you can solve such a problem. So solution. As you can see from the question, you have been told that this beam, the effective span of the beam is 6 meters, and it is spaced at 3 meters center to center. Let's make a sketch here so that you can understand better. So this is the sketch. This is the effective span, which is 6 meters. This is 6 meters, like that. And then these are the beams. These are the beams. Like that. So these beams are spaced at a distance of 3 meters center to center. So this is 3 meters, 3 meters, 3 meters, like that. And remember, from the explanation we have said that center beams are beams which are supporting slabs on both sides. For example, this one is a center beam, so a center beam is a center beam. So let's choose this one. So this one will support a half of this slab and also a half of this. So this will be the area supported by this beam. And this one is an edge beam. So this one will only support on one side. Therefore, you will design it as an L beam. So the area or the width which is supported by this beam is 3 meters. because it is supporting a half of this slab and a half of this. Therefore, it is supporting a width of 3 meters. After having done so, we can as well draw the section of this beam. So to draw the section, let me draw the section here. Now this one is the thickness of the slab, which is HF, and is equal to 150 millimeter. 150 millimeter. And then this is the length of the flange, which is 3 meters. Like that. And here is the rib, or what we call the width of the web, which is equal to 250 millimeter. So this one is 250, like that. And then here is the overall depth, which is 600 millimeter. Like that. We can as well calculate the depths of this, or we can divide this into two. So this one is the slab, and this one is the depth of the beam, which will be 600 minus 150. So this one will be 450. So this one is 450 millimeters. After doing so, you can now start working on the calculation. So this is just the sketch to explain further these statements. So allow me to clean here. We start with loading. So loading on the beam, we'll start by slab self-weight, slab self-weight. So the slab self-weight is calculated as follows. So this one is equal to 150. This is the thickness of the slab. As you can see, this one is the slab. Number one is the slab. Number two is the beam. So 150 over 1,000. Convert this 150 into meters. Therefore, divide it by 1,000. So that is the HF, which is 150. Then times what we call the length of this slab, which is 3 meters from here to here. This is 3. Then times the unit weight of concrete. You are given that in the question, which is 24. Like that. So if you carry out the operation, you will get 10.8 kilonewton meter. So this is 10.8 kilonewton per meter, not kilonewton meter. Then we proceed to beam. Beam self-weight. Beam self-weight. So beam is number 2. You can see from this question, no, from this sketch. Therefore, we'll get the area of the section of this beam, which is 250 over 1,000. Change 250 into meters times the depth is 450. As you can see, 450 all over 1,000. Then times 24, which is the unit weight of concrete, and you will get 2.7 kilonewton per meter. That is the beam self-weight. And then we proceed to the total load on slab. Total load on beam, not slab. Total load. On beam. So total load on beam, we start by the permanent action, which is GK. GK will be the slab self-weight, which is 10.8, plus the beam itself, 2.7, plus, remember we have the finishes, which is 1.0 kilonewton per meter square. It is here. So plus 1.0. Remember this is kilonewton per meter square. So multiply by the distance of this beam, which is 3. By doing so, you are changing it from kilonewton per meter square to kilonewton per meter, because this unit, this 10.8 is in kilonewton per meter, as well as 2.7 is in kilonewton per meter. So you can't just add 1, because 1 is in kilonewton per meter square. So multiply by 3. 3 is the distance which is being supported by this beam from here to here, from here to here, which is that. So you will get 16.5 kilonewton per meter. And therefore, again, we have the imposed load, which is QK. So QK, it is here, which is variable action. This is 2.5. Remember, it is in kilonewton per meter square. So multiply by the distance supported by this load of the slab. So times 3. So this one is equal to, this one is equal to 7.5 kilonewton per meter. So that is the total load on the beam. This is the permanent action, total permanent action, and this is the total variable action. So design action load, which is W, is given by 1.35 GK plus 1.5 QK. So this one is equal to 1.35 times GK is 16.5, then plus 1.5 times QK, which is 7.5, like that. So this one is equal to, if you carry out the operation, you will get W is equal to 33.525 kilonewton per meter. So that is the design load on the beam. And therefore, if you draw the beam, let's draw the beam here. So that is the beam and the loading on the beam. So here is 6 meters spanning, and the load on the beam is 33.5 to 5 kilonewton per meter, like that. From here, we can easily calculate the design moment. And the design moment, which is MED, is equal to WL square all over 8. So this one is equal to W is 33.525 times 6 square all over 8. So this one is equal to, so this one is equal to 150.86 kilonewton meter. So this is what we call the design moment, or the ultimate design moment, as a result of the loading or the design loading on the beam, which is 33.525 kilonewton per meter. And because there is no enough space, I want to clean here, but you can write this somewhere. We have already used this one, and this one, this one, this one, and this one. Not yet, we have not yet used this strength of concrete. You can write it somewhere and then cover. So allow me to clean here. So I want now to proceed to the effective flange width. So effective flange width. Effective flange width. It is found in clause 5.3.2.1 of Eurocode 2, clause 5.3.2.1, and it is abbreviated as BEFF. So that is the effective flange width. So this effective flange width is given by this formula. So BEFF is equal to summation of EFF1 plus BW, whereby BW is the width of the web and BFF1 is the effective width. This one is the effective width on each side of the web determined by BEFF1. So this one is determined by BEFF1 is equal to 0.2 B plus 0.1 L0, and it must be less or equal to 0.2 L0. And L0 is the effective span. So L is equal to effective span. So for simply supported, L naught is equal to 1 times L, whereby L is the length or the span of the beam. So for our case, this one is equal to 1 times L, which is 6. So this one is 6 meters. What about for end of continuous beam? So end of continuous beam, L naught is given by 0.85 L. This is for end of continuous beam, end of continuous beam. And interior span of continuous beam, L naught is equal to 0.70 L. So this is for the interior span of a continuous beam. And then you have the cantilever. L naught is equal to 1.5 L. So this is for the end. This is for the end of a continuous beam, and this one is for the interior span of a continuous beam, and this one is for the cantilever beam. So like that. So if we can go back to our sketch, this is our sketch. So this is BW, which is equal to 250 millimeters, and here is 3 meters, which is 3,000 millimeters. So B1 is equal to the clear distance. This one is equal to, or is a half, the clear distance between adjacent webs. So the clear distance between adjacent webs will take 3,000 minus 250, then divided by 2, such that you can have this distance from here to here, and then from here to here. So the answer is equal to, 3,000 minus 250 divided by 2. So this is 1375 millimeters. So B EFF 1 is equal to 0.2 multiply by 1375 plus 0.1 times 6. L naught is 6, which is 6,000 millimeters, and it must be less or equal to 0.2 times 6,000. So this one and this, it will give you 875 millimeters, which is less than, then 0.2 times 6,000, you'll get 1,200. Therefore, okay. Therefore, B EF1 is equal to B EFF2, which is equal to 875 millimeters. So BEFF1 is equal to BEFF2, which is equal to 875 millimeter. Remember, this BFF is the effective flange length on either side of the web. So allow me to clean here. You can write this somewhere. This is the ultimate design moment, which is 150 kilonewton meter. So write it somewhere. Now let's continue. To calculate the effective flange width, is equal to, the formula is there, summation of BEFF1 plus BW. So the summation, it means the BFF1 and the BFF2, which is equal to 875 plus 875 plus BW, which is 250. So this one is equal to 2000 millimeters. So this is BEFF, which is the effective flange width. So remember, this 3000 is not the effective flange width, but it is the breadth of the flange. This is the one that will be used in our calculation. Therefore, from there, you can now determine the effective depth. Effective depth, which is D. So for us to calculate the effective depth, you will say that assume main bar diameter as 20 millimeter and the links or link as 10 millimeter. Therefore, D is given by this formula H minus cover minus link diameter minus a half diameter of main bar. This one is equal to, the H is from here up to here, which is 600 millimeter. So this one is 600 minus cover is 25. We have been given the question. And a diameter of link, which is 10, minus main bar, which is 20 all over 2. So the answer will be, the answer is 555 millimeters. So to explain further how to determine this D, if this, let me use this one, if this is our main reinforcement, then from a half of this diameter to the compression side, that is D. And remember, we have the links, as you can see. So you will take 600 minus cover, this is cover, minus diameter of link minus a half of this, you will get 555 millimeters. So we know that K prime is equal to 0.167 and K is equal to MED all over FCK BEFF D square. So this one is equal to MED is 150 point. Is 150 point. Let me check. 0.86. 0.86 times 10 to power of 6. Change it from kilonewton meter to newton millimeter over FCK is 25 times the effective flange width is 200, is 2000, not 200, is 2000 times D, 555 square. So this one is equal to 0.0098. So this is K. Therefore, K is less than K naught, which is 0.167. It therefore imply no compression steel or reinforcement is needed. Therefore, design as a singly simply supported beam. Instead of using K and K prime, you can as well use this one, moment of resistance MRD is equal to 0.167 FCU BD square, and then you multiply by 10 to the power of -6, so that you can have your answer in kilonewton meter. And therefore, after getting MRD, you'll compare MRD with MED, whereby MED must be less MRD for no compression steel to be used, and also for a singly reinforced design beam. So that is it. Now let's calculate the neutral axis, which is X. So X is equal to D minus Z over 0.4. Why are we calculating this X? It is important to calculate X because it will help us to know if we will design this beam as a rectangular beam or as a true T beam. Remember, if X is less than HF, whereby HF is the thickness of the slab, so this is HF. So it means the neutral axis is in the slab. So it means the neutral axis is in the slab, like that. So we will design this as a rectangular beam. But if X is greater than HF, it means the neutral axis, it now changes. The neutral axis will be now in the neutral axis will now be in the web. So this is X. So for this, you'll use different formulas for area of steels. So let's check if X is in the HF or is in the web. We know that D is equal to, D is equal to 555 millimeters, and the Z is equal to D 0.5 plus 0.25 minus 3K all over 3.4 raised to power 0.5. So Z is equal to D is 555, 0.5 plus 0.25 minus 3 times K. K is here, 0.0098 all over 3.4. Remember, this is over a half, or 0.5. And then multiply everything by D, which is 3.5. So we have 0.25 minus 3 times 0.0098 all over 3.4 raised power a half, or 0.5. Then plus 5, 0 plus 0.5. So this is equal to 0.99 times 3.5. This is beyond the limit. So the limit, it should be less or equal to 0.95 D. So if it is beyond the limit, then we adapt 0.95 D. So 0.95 D is equal to 0.95 times 3.5, which is equal to 0.95 times 3.5. 527.25 millimeters. So make it 527 millimeters. So this is Z is equal to 527 millimeters. So X, you go back to X is equal to D, which is 3.5 minus 527 all over 0.4. So this is equal to 70 millimeters. So this 70 millimeters is less than HF, which is 150 millimeters. So this HF is the thickness of the slab. Therefore, the neutral axis is in the slab. So if this neutral axis in the slab, you will design as a rectangular beam. So the formulas remain the same for the area of steel in tension and compression. But if X is greater than HF, then you'll design as a true T-beam. Remember, it is important to check where the neutral axis is falling, because for X is greater than HF, the neutral axis is in the web, and therefore you will design as a true T-beam, and the formulas will change. The formulas for area of steel in compression and tension will change when X is greater than HF. But since our case 70 millimeters, which is X, is less than HF, which is 150, we are going to design as a rectangular beam, or we design as a T-beam, but not a true T-beam. So remember, area of steel is given by this formula, M ED over 0.87 FYK Z. So this one is equal to, area of, design ultimate moment is equal to 150.86 times 10 to the power of 6. We are changing it from kilonewton meter to Newton millimeter times 0.87 times 500 times Z. Z is 527. So area of steel is equal to 658 millimeter square, and therefore provide. I hope you know how to read the table. Provide 3H 20. Area of steel provided is equal to 943 millimeter square. Then after there, we will check the area of steel is equal to 0.26 FCTM BWD all over FYK. So this one is equal to 0.26 times 0.3 times 25 raised power 2 over 3 all over 500, then times BW is 250, that is the breadth of the web, then times D is 555. So this one will give us 185. And remember, FCTM is given by this formula, 0.3 FCK 2 over 3. Yes, it's given by this formula. This one is given by this formula. FCK, which is here, 0.3 times 25 raised power 2 over 3. Millimeter square. From there, we again check for 0.0013 BT. So this one is equal to 0.0013 times BT is 250. This should be TD times, so the under is equal to 180 millimeter square, and then 0.04 AC is equal to 0.04 times H. AC is the area of the concrete in the section. So the section is 600 by 250. So this is 600 by 250. So this one is equal to, no, the section is 450, not 250. This is 450 times 250. So this one is equal to 45. 100 millimeter square. Therefore, AC is less or equal to 0.04 AC. This is area of steel, which is greater than 0.26 FCTM over FYK, and it is less or equal to 0.0013 BTD. As you can see, this one is 4500 and area of steel is 658. Here is 185 and here is 180. Therefore, okay. Proceed to minimum bar spacing. For the minimum bar spacing, clear distance between bars. So the clear distance between bars, if this is our beam, and we have 3 bars here, like that. So to calculate clear distance, we'll take this distance, which is 250. So 250 minus the cover, which is 2 times 25, minus distance, minus the diameters of these 3 bars combined. So this is 3 times 20, and then we'll divide by the number of spaces. We have 2 number of spaces, this is 1 and 2. So 3 minus 1, which is 2. And our answer will be, let me do the operation. So this is 250 minus 50 minus 60 divided by 2. So this is 70. This is 70 millimeter. And this 70 millimeters, must be greater than minimum of DG plus 5 millimeters, and then the size of the bar, and 20 millimeters. So DG is the aggregate size, which can be 20. So 20 plus 5, this is 25 millimeters. And then the size of the bar is 20, and then 20. So 70 is greater than 20 millimeter, therefore, okay. So clear distance between bars is okay. So we proceed to shear reinforcement. So for shear reinforcement, we'll first calculate VED. So this one is given by this formula, WL/2. So our W is the loading, is the ultimate loading on the beam, which is 33.526 times 6/2 So this one is equal to 100.58 kilonewton. And therefore, we will calculate design shear at distance D. Design shear at distance D. So if this is our beam, so it is loaded with 33.526 kilonewton per meter. Remember, it is simply supported beam spanning 6 meters. So if we can draw the shear force diagram, so this is the shear force diagram. So this is VED, which is equal to 100.58, the same as to this, 100.58. So let's calculate design shear at distance D. So let's assume this is distance D. This is distance D. Because this distance is more critical when it comes to shear. This is D. So we want now to determine VED. VED at distance D. So we will take, this is the reaction, or VED, which is in the upward direction. So this is 100.58, then minus the loading. So we can bring here the loading. Here it is, which is 33.526. Because it is in the downward direction, it's a minus. So minus 33.5 minus 33.526 times distance, which is D. This is 555 over 1,000. So you will get 82. So shear force at this point is 82 kilonewton, like that. Now VRDC is given by this formula, and this is the shear resistance of concrete. This is the shear resistance of concrete, like that. So VRDC, which is the shear resistance of concrete without reinforcement, is given by this formula, and VRDC, it must be greater or equal to V min plus K compressive stress into bracket times BWD. So VRDC is equal to, if you can break this down, VRDC is given by 0.18 divided by a factor of safety for concrete, which is 1.5. So 0.18 divided by 1.5, you get 0.12. And then K is given by this formula, 1 plus root of bracket 200 over D. So this one is equal to, our D is 555. So this is 1 plus 200 all over 55 raised to power 0.5. You get 1.6. It must be less 2.0, which is okay. And then this one is given by area of steel, which is 943. BW is the breadth of the web, which is 250 times 3.5. you will get 0.0068. So 943 divided by 250 times 3.5. So that is 0.0068, and it must be less than 0.02, which is okay. So this one is for no axial load, so it therefore is equal to 0. So in our formula, here it is, this one is equal to 0 because no axial load. So this is as a result of axial load. It is a compressive stress as a result of the axial load. So it's equal to 0. So we'll ignore this one. So K times 0 is 0. So let's now insert the values in this formula. So CRDC, you already have it, 0.12 is here, times 1.6, which is K, open the bracket, 100 times 0.068, it is here, times FCK is 25, and then this one is power third, times BW here it is, this one is the breadth of the web, which is 250, and then D is 550. Then you'll multiply everything by 10 to the power of negative 3 so that you can have your answer in kilonewton. So if you carry out the operation, you'll get 68.50. So let's check. 0.12 times 1.6 times 100, times 0.0068 times 25. This is raised power a third. Yes, you get 68.50 kilonewton. And then V mean BWD, this is equal to, again, here, this one is equal to 0 because we have said that there is no axial load, which will imply this one is equal to 0. So we'll remain with V mean times BWD, like that. And V mean is given by this formula. BWD remain the same. So K, you already have K, 1.6, FCK is 25, then BW is 250, D is 555. Then convert it from Newton to kilonewton, so times 10 raised power negative 3. You will get 49.14 kilonewton. As you can see, VRDC is greater than V mean, therefore K. Since VRDC, which is 68.5, is less than VED, which is 100.58, shear reinforcement must be provided. So shear reinforcement must be provided. Now let's finalize on these shear reinforcements. So VRD maximum, let's calculate the VRD maximum, and this is the compression capacity of compression struts, assuming theta is equal to 21.8 degree. So VRD max is given by this formula. BW is the breadth of the web, and Z is 0.9 D, and then V is given by 0.6 into bracket 1 minus FCK over 250, which is equal to 0.6 minus 25 over 250, you'll get 0.54. And then FCD is given by this formula. Alpha CC is 0.855 times FCK, which is the strength of concrete, which is 25 over 1.5, partial safety of factor for concrete, and you will get 14.2 Newton per millimeter square. So VRD max, if we insert these values in the formula, we'll get 330.2 kilonewton. Remember to multiply everything by 10 to the power of negative 3 so that you can have your answer in kilonewton. Since VRD max is greater than VED, then it is okay. Then we proceed to shear reinforcement. Using the shear force at distance D, you remember this, you calculated and we got our value as 82 kilonewton, and cot theta is equal to 2.5. So ASW over S is equal to VED over Z FYWD cot theta, whereby FYWD is 500 over 1.15. 500 is the strength of steel. This is 500 Newton per millimeter square. And 1.15 is the partial safety factor for steel. So you'll get 435 Newton per millimeter square. Then ASW over S, we use the shear force at distance D, which is 82, convert it to Newton. You'll get 82, multiply by 1,000, you'll get 82,000 over 500 times 435 times 2.5, you'll get 0.151. Let's go for minimum shear reinforcement check. So minimum shear reinforcement is given by this formula, 0.08 FCK raised per half over FYK. FCK is the strength of concrete, which is 25. FYK is the strength of steel. So you'll get 0.008. Then minimum ASW over S is equal to a minimum reinforcement times BW. So this one is 0.008. That's 0.8. Let me check. 0.08 times 25 raised power 0.5 divided by 500. So the answer is 0.00, not 0.0008. So 0.008 times 250 times 250, this is 0.20. So since if you compare these two, this one, the one calculated from the shear force at distance D is 0.151, is less than 0.20. Then we use the minimum requirement, which is 0.20. So let's try H8 links. These links, we give it two legs. Two-legged, the area of this steel is 101. So this area is obtained by area, the formula for area is pi d square over 4. So you'll take pi times d. D is 8. 8 square. How many are they? 2 times 2 all over d. No, all over 4. You will get 101 millimeter square. So required spacing is 101 over 0.20, which is 500 millimeter. This is beyond the limit. So maximum spacing, this is the maximum spacing, is 0.75 D. So D is 555. So 0.75 D is equal to 416 millimeter. Hence, the limit in the table is 300 millimeter maximum. So we use 300 millimeter. So hence provide H8 links. So provide H8 links at 300 millimeter center to center throughout the beam. But you can reduce the spacing. You can reduce the spacing as you approach the support to 250 millimeter. You can reduce the spacing as you approach the support to 250 millimeter center to center. And that marks the end of today's example or today's topic, but the question is not complete. If you can finish the question it will be good, so that next time I don't do the same question. So I'm remaining with a deflection, and then detailing, and then the sketch. So I hope you can finish the question, you can finish up the question, so that next time don't repeat the same question. So thank you for your time, and let's meet again in my next session. And for those who are not subscribed to the channel, please subscribe and hit the notification bell, so that you may be the first person to be notified. Thank you.